Apologies for not having a video yesterday as we should have had, but yeah, sometimes my work takes more time than our YouTube schedule supposes it to take. So yeah, but today we'll take a look at two problems that we were supposed to take a look at yesterday. The both come from an educational round, namely 109. And they are quite nice, I must say, because I really like the mathematical part of these problems, so yeah, quite enjoyable ones to solve. And the first one is only problem C, but already 2000 rated, because the observation may be not obvious to make. That solves the problem. So let me tell you the short version of the statement. We have n robots on x-axis, so like on a number line. However, they are limited by two endpoints, one at x equals 0 and another one at x equals m. They start in positions xi, and each of them moves either to the left or to the right. And the legend says that when two robots meet at the same integer point, they collide. For example, here we can see one possible example. That is actually a really great hint towards the solution. And what we are required to print is like, what is the time when the robot will collide with something else? Or -1, it will stay if it will stay on forever. So yeah. Like specific number of points you can see, number of robots you can see here, however m is quite large, so you got to manage that accurately. So yeah, the problem is very simple. Like you just have robots, they move to the left, to the right, and sometimes they collide, and sometimes they bounce off the walls. So this number 6 moved here, and then when he arrives at one of the endpoints, it changes its direction of movement. So yeah, so it's extremely simple. It reminds me a lot of this, like, you know, ant-related problems in math, when like two ants, when they meet, something happens. Well, apparently, like exploding ants was not great, not very humane. So that's why we have exploding robots. But other than that, very similar spirit of the problem. Now, first of all, I kind of questioned myself, like, when two robots actually can't collide. And turns out that this can only happen when the distance between them is an even number. As you can see, 1 collides with 3, 2 collides with 4, and 5, interestingly enough, collides with 7, despite they are moving in the same direction initially. Because obviously at some point 7 is going to turn and then they collide, as you can see here. So yeah, that condition was like a strong candidate into partitioning all robots based on whether they start initially. If their initial coordinate is even or odd. And we can formally prove that the robots with different parity of initial coordinate will never collide. The proof is as follows. So like imagine you have two robots. There are several cases we need to consider. First of all, they both can be moving to the right. In this case, I want to reason in terms of this distance. And what I'm saying is that this distance has not changed if they are moving in the same direction. So like delta of this distance is equal to 0. And the same happens if they are both moving to the left. Distance does not change between them. However, there are two more cases. So first of all, they can move towards each other. So like this one's moving to the right and this one's moving to the left. And in this case, I say that the distance between them decreases by 2, right? Well, like every second. And the final case is that they may be moving further apart from each other. In this case, you may think that they won't collide, but potentially they actually can, as we will later see. Because the delta between them is +2. So like each second they become 2 units of distance further apart than they were the previous second. And based on this, we can see that the parity of distance between 2 robots never changes. And therefore 2 robots which initially had odd distance between them can never collide, because 2 robots collide when the distance between them is 0. Yeah, sort of discrete continuity here. Like you can't get 0 if your steps are 2 and you're starting in an odd point initially. So yeah. So after this observation, which we formally proved quite nicely, I thought let me do the following. Let me classify all robots into 2 parts based on like their initial coordinate. So I will have, so this one will be odd, and this one's odd, and this one's odd. And all even guys, they will go into a different group. And I want to see what are their initial directions to figure out who will collide with whom. This one's moving to the right, actually. This one's moving to the left. Both of these are moving to the right. And then here they are moving to the right, left, and this one's moving to the right. Well, first things first, you can see if 2 guys are moving towards each other, then they basically collide with each other. Like, because there is nobody in between them with whom they may collide. So yeah. Whenever you see 2 robots consecutive, like of the same parity that are initially moving to the right and left, they collide with each other. Obviously, you can just compute the distance, divide it by 2, and get the time of the collision. All right, so like this situation we just cancel out. However, more interestingly, you can see that here we have 2 robots there that are moving to the right. They have no robots moving to the left further up the road, and therefore they collide with each other. And this always happens. Like if there was a robot here or even here, it will collide with this one. Because at some point, like here, it will move here, right? No, like initially it's moving here, then it's moving here, then it's moving here, and then here they collide. And this always happens. It's not like a special case or anything. When you have 2 robots that are moving to the right, that are like last 2 robots, then they collide with each other. And you can compute like the total distance that they will travel before collision. They will travel like this distance for sure. And then also something like this distance. We don't know which one will travel which part, but in total they will travel this part. So what happens is we take just sum of these 2 distances and divide it by 2, because each like a unit of time, there are 2 robots, each one is moving at the speed of 1 unit per second, so together they are moving 2 units per second. So yeah, so we figured out that we can cancel out right left whenever we see it, right when it's the last part, and well, by analogy, right? Like the same way we can cancel out 2 robots moving to the left if there is no one to the left of them. So like we could to have, let's say this one's also moving to the left. Well, that's clear. That should be clear that its situation is the same as this one, right? They're just moving in the opposite direction, but they will still collide. So yeah, once you consider this, like you can cancel out most of your robots. There are 3 cases that you can't cancel out. First of all, you can have 1 robot remaining because it got no pair. Well, in this case, like, well, it will travel forever, like this number 6 here. So that's 2 cases. Another case that you can have that does not have such a prefix of left, left, a suffix of right, right, or right, left in somewhere in the middle is left, right. So like only 2 robots, one is moving to the left, another one is moving to the right. Turns out they will still collide. They will collide once both bounce off the walls. They will collide somewhere in the middle. And we can also compute the total distance they traveled. So like this traveled this part, this traveled this part, and then together they traveled this. We don't know, once again, where exactly. We don't need it to calculate exactly where they will collide. We just take all of these 3 distances and divide it by 2. So yeah, so this case they also cancel out when they are the last ones standing. And these guys travel forever. So now we just have to come up with translate this logic from math to programming. Well, obviously we talked about like robots being consecutive, so that clearly means that we need to sort them. We also need to like split them into 2 groups based on oddness of their initial position. And once we did it, like we basically scan the robots and look for these patterns and eliminate them whenever they appear. So yeah, now it sounded to me like a stack is a good idea for such eliminations. Like you basically matching brackets left with right or something like that. That's why I thought that a stack is a good idea. And this is exactly how I implement it. So I guess there is not much to say about mathematical part. We like formally proved everything. And this nice trick with distances should be also clear. So I guess that's like why problem setters decided to place it as C, because you just figure out like simple ideas and then you get the solution. I understand that it can be tricky to get it. I totally do. So yeah. Not exactly sure why it's 2000 rated, but like rating does not come out of nowhere. So apparently some people struggled with it. So yeah. I hope it was like with mathematical part of the things, because implementation side it's not particularly difficult. I actually decided for this one and for the next one to have like a very readable code. I don't know if it really helps, but hopefully it does. So because we are working a lot with robots, we'll create a structure for them. It has like default constructor and also operator less for sorting. And by the way, I realized, I was told today that in C++ 20, which is coming to Codeforces soon, for simple structures like this, you won't need to implement comparison operators yourself. You'll be able to like use a default spaceship operator, which consequently derives all 6 two-side comparisons. That's great news, because sometimes it's really annoying to write operator list for your structure, because most of the time you just want to compare them in the lexicographically in the order that fields are specified in the declaration. So yeah. So here, and you can also unpack structures in C++17. So there, this structure is just a nice wrapper around the tuple. Like you could have used the tuple of int, char, and int, but you can also use a structure. It will also have structured binding syntax. So yeah. And as you can see, the names don't have to coincide. Just because I could not use the single underscore twice, I decided to make it this way to signify that it's unused here. And we fill in the indices, we sort, then we'll do our stack processing. We have 2 stacks, so I decided to use an array of size 2. We could use a vector, that does not really matter. And we loop over all robots. First of all, we always go to the right stack, which we can take as this. In general, I believe it's kind of obvious that you can check if the number is odd or even by taking bitwise end with 1. So we check if the stack is not empty. If it's empty, then we just in place. Otherwise, we try to cancel out patterns such as left left and right left. We can do it simultaneously, because if we cancel all right lefts, and whenever we encounter left left, it means that these are in the prefix. Actually, two first letters are left whenever we encounter such situation. However, we don't cancel out right, because that is something that we can't do before we came to a suffix. So that's what happens here. As long as it has enough characters, we can take 2 from the end. And as you can see, they are always right, as they should be. Then we have just one special case of left right that gets processed in a special way. Or it can be actually right that just haven't got processed here because of the way I wrote this condition, basically. So yeah. And if we are left with one robot, that it won't ever collide with anyone, so it gets -1. And also you may have noticed that a lot of time I use construction like this, answer at some index gets answer at other index gets something. Because basically these 2 guys collide with each other, so the answer for them is the same. And then I compute the answer. This works, I believe it first assigns here, and then the result of each assignment returns something, and this value can be later used in this assignment. So just to save you some code, you can use like this. But you should be careful when chaining operators. Does not always behave the way you expect, but with assignments I believe it's fine most of the time. And here there are just specific formulas based on position of the top of the new robot and position of the top element in the stack, depending on what orientations of these robots we have. The way we compute the time until collision changes a bit, but not much. So yeah, hopefully this is readable enough for you to get through the details yourself. There will be a link to this submission down in the description box as always. But that's kind of it for this problem. That's all I wanted to share. I think it's nice mathematically. Not so nice with implementation, but I believe I just like this. Let's face it, this code is a little bit verbose because I believe it's better this way than when like everything is, every variable is 1 letter long, and sometimes it may be hard for you guys to like understand what's going on. Especially if I did not explain all the details of the solution in the theoretical section. So yeah, how this helps, we'll see. Another problem that I wanted to show is problem E, and that's because problem D we actually seen in a video already, I believe. This was another nice problem I got almost first try. Was not careful enough. And this is a probability theory problem. And it's about one of my favorite games. Assimilation IV, as you can probably guess, is a reference to Civilization IV, and especially those monuments that were super strong. Like you could get a lot of area by just having high culture. So like back in those times, it was very profitable to be a man of high culture. So yeah. And actually in this problem, monuments are even stronger than in the game, because in the game you are getting like for each next level you had to wait more time, I believe. Like you needed to produce more culture for the boundaries of your city to increase, and the culture for each next level, for each next tile, I believe, was linear, so the total was quadratic, and that was kind of tough once you controlled to control more than, let's say, a radius of more than 7 tiles. It was a little bit challenging to control, but yeah, it was possible, I guess. Sorry for that like short trip to the past. I used to play it a lot in the high school, so probably that's why I don't have like gold IMO medal and only silver. But yeah, it was worth it, I think. So the way it works in this problem is that we have n cities and m points that we want to control, and when you build a monument, it initially controls points within distance 1, and then each turn the distance increases by 1. You are given the distancing matrix from each city to each point. Not sure if it obeys Euclidean laws or Manhattan laws, whatever was actually used in Civilization. I believe Manhattan sounds like more reasonable approach. We don't have first. So yeah, and we want to calculate what is the expected value of how many points we will control. Expected value comes from the fact that we choose the order in which we build monuments randomly. Dude, I'm explaining this problem like very badly. You should just pause the video and read the statement if you want like full details. But I'm trying to give like a broad idea of what's going on. So we have like cities, and we have points that we want to control. We choose the order in which, we build the monuments is random. And then by turn 5, like this controls a large circle, this controls a slightly smaller circle, this one smaller, and then this one controls like very small circle. The distances need not be Euclidean in like 2D actually all distances are Euclidean if you take high enough dimension, but whatever. And as you can see, like in this case, we control this point, and we don't control the other points. We are interested in like what's the expected value of how many points we will control when averaged over all possible permutations in which order we build the monuments. That's like broad idea. And of course, when dealing with expectation, like they tell us that the expectation is a fraction that we want to compute modulo some prime number. That I assume that you know how this works. That's kind of basic already for now. By now, like it was a little bit tricky like several years ago, but now I've seen a lot of expectation in probability theory problems. This does not come as a surprise for me. So yeah, of course, when talking about expectation, we want to use the linearity of expectation. There will be a link to it down in the description box below. But the basic idea is like the expected value or the expected number of points that we will control is the sum of probabilities that we will control each point. And it doesn't matter that these events of controlling points I and j are dependent. The linearity of expectation always works. You can read the proof and more details following the link in the description box. But if you know what I'm talking about, then it should be clear that we like have to process each point on its own. And so basically what the problem we are left with is like what's the probability that we will control each point. Unfortunately, points are given like as columns of this thing, so not very nice, but still acceptable. So the problem that we have at our hands is we have some point and then distances from it to all cities. And we want to somehow efficiently compute how many permutations result in this point being controlled. And here I started thinking like usually, or not usually, but quite often in such problems, the probability of like getting controlled is difficult to compute because the event that like point I, point j is controlled is actually the union of events point j is controlled by first city, point j is controlled by second city, and usually unions are not nice to deal with. So what's much nicer is take the conjugate of this event, like compute the probabilities that point j won't be controlled, because it means that it won't be controlled by the first city and it won't be controlled by the second city and etc. So intersections are generally better when you're working with probability because intersection means multiplication of probabilities usually, if they are independent. Or here they are not independent, so but it's still better to compute the probability that we won't control some point. So now let's take a look at like these things and think about like what's given like some column of this matrix. I want to figure out what's the probability that we will control some point. And I came up with a very nice visual explanation of how this works. I will redraw it from here. So I decided to like to portray all of this on a n by n grid. And the way it works is as follows. So let me just draw it first, because it will be so much easier to understand when you see it. These are the points from the statement, from the sample. You can try to think how we ended up here, because you should probably be wondering in this moment. Yeah, but like this specific sample illustrates very well what is going on. So the samples are like this. So first of all, technically it's not nice that the distances start with 1, so I reduced all the distances by 1. Now they are from 0 to 3. And then so first is 0, 0, 0. So I take zeros and I draw 0 squares in each row. And I get 3, 3, 3, and I draw 3 cells in each row. And I get 3, 0, 3, so I drew 0, 3, 3. You can see that they are sorted. Here 2, 3, 3, so 2, 3, 3, and 1, 2, 3. This illustration is extremely helpful in coming up with like how many permutations don't control some point, because of the following observation. Let me draw a little bit more. And also let me draw this. So my idea is actually if we have some distance, right, from I city to J's point, what it means, like where can city I come in our permutation? We don't want the point to be controlled, so it should not come very early, because then it will reach the radius of the monument will reach this distance and it will control the point. So what we want is like we want it to come late. So we want it to come on some suffix. Like here it can't come, here it can be. And the length of the suffix is of something like n minus distance. Because of distance, no, the length of the suffix is, I believe, dij minus 1. Because if distance is 1, then it will always get controlled. That's why we have like minus 1 here. Yeah, so that's like the length of the suffix when we can use this city. So that's like they are actually placed as suffixes at the moment. The length of this suffix was 3, this 2, this 1. So they are just very visually stacked together quite nicely. And once we have this, I was thinking like, okay, so basically we need to choose the order in which we visit our cells so that like we don't end up in a bad place, all right? So I was thinking like, okay, so I can choose something like here I have only one choice, and that is to use this, right? Not great. But at the same time, it's kind of easy to compute. So here, like only one way. Here I was thinking, okay, so I can use this, then I can use this and this. So that's one way. But I can also use this. Technically, then I will need to use this, right? But in terms of how many ways I have, this actually gets embedded quite nicely into how many blocks there are on or above the diagonal. Why? Why so? Because actually, like, you can take only 2 guys here, you can take 3 guys here, but you already taken one of them. So you say like, okay, 3 minus 1. And this 1 is exactly what you cancelled out here. So that's why you are not taking blocks under diagonal. And then here you can also take all 3 guys, potentially. But you already used 2 of them. You don't care which 2, because in all cases you are left with 3 minus 2 ways to choose them. So that's, and same with other guys. Like sometimes you have like, you don't have blocks above the diagonal, so you can get just multiplier of 0, and therefore the probability of not controlling the point is 0, because the set of distances is small. So yeah, but in general, like, this is something we get. So here we get like 0 times 0 times 0, which is 0. Here we get 3 times 2 times 1, which is 6. Here we get 2 times 1 times 0, which is 0. Here we get 2 times 2 times 1, which is 4. Here we get 1 times 1 times 1, which is 1. If you read the explanation of the sample carefully enough, you will see that this point is controlled in all 6 case permutations. This point is never controlled. This point is always controlled. This point is controlled in 2 occasions, namely here and somewhere here. It's point number 4. This point is controlled on all occasions but 1. This is point 5, and it's not controlled only in this permutation. So you can see how these values complement each other, which makes you believe that this actually works. But yeah, the formal proof is that you have like however many values you got in your column, but then you have to subtract 1 because you already used it. So that's like quite common pattern in combinatorics. When you want to count some permutations, you often don't care about the actual permutation, like what you've taken already. You only care in how many different ways you have at this moment, and often it does not depend on the choices you made in the past, like here. It does not matter which one of these 2 guys I choose, the other one will be available for the next operation. If I choose this, then this will be available. You got the idea. So now we just have to like compute this efficiently. Of course, you can do it in quadratic time. I did it in linear time. So yeah, for the overall complexity of just O of nm, more or less O of nm, and we'll see why not exactly a bit later. Because like technically we have to do modular arithmetics by multiplying over this. This value is actually like the denominator is always just a factorial. So yeah, you actually only have to take 1 modular inverse, but technically that should be included in the complexity, if you're very careful about that. Yeah, I understand that this is just very smart interpretation. I'm proud of myself for finding it like a lot. The last time I remember seeing something like this was in high school when at some mass training camp we were talking about, I don't remember the name, but there is like a name to such diagrams, Young diagrams or something like that. They help count a lot of things when you just like have sorted shape that is sort of affected by gravity. So yeah, I just remember that thing, and it was like very nice. A lot of memories this problem brings. But yeah, I assume that by now you already want to see the implementation section. I had only one like small bug when I did not mod properly. Let's take a look at this submission that contains no bugs. So as already announced, we have to deal with modular arithmetic. Basically, we need to compute modular inverses. For this, in turn, we need modular power, because inverse is completed like this via Fermat-Little theorem, probably known. And this is input, and the actual solution is very short. First of all, we need the factorial because we will multiply by inverse. In my bug, by the way, was not taking this plus mod because like sometimes expectation was negative because I did not mod properly. But yeah, then we loop our points. For each point, we'll compute the probability of it not getting selected. So the probability, like we constructed frequency table instead of constructing the entire matrix explicitly. Constructed frequency table, and I just like I'm able to quickly count how many how many cells I have in each column without constructing the entire grid. I just keep a prefix sum, that's how many rows I've seen already. And this is like how many rows I already used. So yeah, for this one I needed frequency table, so that's why we have this. So yeah, like for something that looked like this, if you remember, I will just give one example. Like here, the frequency table is like, we have 2, 3, 3, so the frequency table will be 0, 1, 2, 3. Frequency table is 0, 0, 1, 2. And this, yeah, as you can see, we scan from right to left, so we'll go and see like, okay. Here we have 2 options, so let's remember that. Here we get one more new option, so like the prefix sum is 3, but we already used one of these 2 guys here, so that gives us another multiplier of 2. Here prefix sum is still 3. We used already 2 guys, so we get a multiplier of 1. We take 1 times 1 times 2 for a total of 4, so the same value we computed previously. Yeah, however, this is a probability of not being controlled, so the probability of being controlled is factorial minus p. Or like 1 minus probability, but keep in mind that we will only divide by factorial once at the very end. So yeah, this value can actually be negative if factorial is too large, like mods out. And if this is negative, then expectation can be negative and does not have to get back while we mod. So often in such cases, I like not to think about whatever happens here. Like I'd like to just carry out all computations with potentially negative numbers, with potential negative long numbers that will never overflow. Just remember to mod and then remember to plus mod at the end. Unfortunately, this time I forgot, so I got wrong answer 26. But it was kind of obvious that I needed to do this, so fixed it within 1 minute. Yeah, very nice problem, enjoyed it a lot. Recommend solving it if you haven't already. So yeah, once again, sorry for not releasing this video yesterday, for not recording it yesterday. I was really busy at work. I hope it will not become our permanent feature. I wonder when I will be able to actually take a look at the problem schedule for today. I hope it's somewhere today in the evening, so maybe we'll have a video, 2 videos today, but maybe not. Let me actually start working today, and then I will be able to estimate when we'll have a next video. But yeah, in case of any further delays, I'll always let you know on the community page. I haven't really used it before. I think it's a very nice way of communication. And also I've got some comments, like people not being able to suggest problems in the comment section down below. In this case, you can message me in my Discord server. The link will be somewhere, probably there. Yeah. So yeah, if you haven't joined, you're welcome to join. We're not very active there. We just hang out, occasionally discuss some problems. So yeah. Potentially, I'm not always able to answer your questions quickly, but other Discord members may answer them quicker than I do. So yeah. Thanks for watching. I hope you learned something new, because today's episode was quite nice in terms of mathematics behind the competitive programming. And I'll see you soon. Bye bye, guys.